The authors propose an extended neutrinophilic 2 Higgs doublet model, 2HDM, to establish a connection between the muon anomalous magnetic moment, g2, mu, and neutrino masses. Building upon previous neutrinophilic 2HDMs and type IB seesaw models, which address the smallness of neutrino masses through suppressed vacuum expectation values, they introduce an additional charged singlet scalar. The novelty lies in utilizing right-handed neutrinos to generate neutrino masses, while incorporating an enhancement mechanism that significantly contributes to the charged lepton anomaly via loops. The development focuses on specific case studies, such as lept1 EF lambda K32 Cre EE She Eta stopic, to resolve major conflicts surrounding high Majorana neutrino masses, MVR, while incorporating right-handed, RHR, influence. The model explicitly associates masses with current-day constraint responses, allowing for interesting predictions within a relative perspective. By assessing the parameter expressions involved, the authors demonstrate consistency over a range of associated degrees, thereby extending bounds on light neutrino masses. The interaction coefficient changes are key to understanding the cross-section bounds, particularly in the context of charged lepton flavor violation. The model provides a clear distinction between different contributions, enabling a better understanding of weak and strong constraints. The author's approach, which considers the charged lepton flavor violation, offers a more comprehensive analysis than previous models. By considering the full neutrino sector, the model explains the observed anomalies, providing a more complete understanding of the underlying physics. The refined model presents a novel explanation for the muon anomalous magnetic moment, g2, mu, and its connection to neutrino masses, offering a more precise understanding of the underlying mechanisms. The anomalous magnetic moment of the muon, denoted as g2, micro, remains a significant discrepancy between experimental measurements and standard model predictions. The current experimental value stands at AEXP micro equals 11,659,205.9 plus or minus 2.2 times 10 carat 10, while the standard model prediction from the muon G2 theory initiative white paper is ASM micro equals 11,659,181.0 plus or minus 4.3 times 10 carat 10, resulting in a 5.1 sigma discrepancy of delta ABSM micro equals 24.9 plus or minus 4.8 times 10 carat 10. This discrepancy can be addressed by introducing minimal extensions with one or two new fields, avoiding large charged lepton flavor violation effects. New physics explanations for a micro require chiral enhancement, achieved by replacing one chiral flipping coupling involving the muon Yukawa Y micro with an order 1 coupling. At the TeV scale, the dipole operator responsible for a micro is given by the dimension 6 operator L micro sab H micro RF ab in the electroweak symmetric phase. The one-loop contribution to a micro can be separated into two classes, depending on the location of the Higgs insertion. Type I contributions involve Higgs insertion in the external muon legs, with no chiral enhancement due to the accompanying muon Yukawa Y micro. In contrast, chiral enhancement is possible for type E contributions, where the Higgs insertion occurs in one of the internal lines. Notably, the dispersion method and lattice results reported by the BMW collaboration disagree, with the latter reducing the A micro discrepancy to 1.5 sigma. An investigation of the source of incompatibility between these approaches is urgent, and high-precision lattice results are required to resolve this issue. In this work, the result in EQ1 is adopted. The anomalous magnetic moment of the muon, AMU, can be enhanced in various beyond the standard model BSM scenarios. One such enhancement occurs when the Higgs insertion is replaced by the top or tau Yukawa coupling, or through non-standard model interactions, such as with vector-like leptons. In two Higgs doublet models, 2HDM, and the minimal supersymmetric standard model, MSSM, new scalars mixing with the SM Higgs can also contribute to AMU enhancement, but require specific conditions and constraints to accommodate AMU, including TeV scale mediators and interplay with charged lepton flavor violation, CLFV. The paper also explores the connection between AMU and neutrino mass generation, focusing on TeV scale mediators and seeking minimality in their number. Lowering the mediator masses in Type 1, Type 2, or Type 3 seesaw models does not enhance AMU due to a negative contribution. Instead, alternative ways to lower the seesaw scale are considered, such as the inverse seesaw, radiative generation, and attributing the smallness of neutrino masses to other factors. The authors conclude by discussing the potential for connecting AMU with radiative neutrino mass generation, highlighting the need for a correct sign of the contribution in Type 2 seesaw models. Overall, this study sheds light on the enhancement of AMU in BSM scenarios and its connection to neutrino mass generation, providing valuable insights for future research in these areas. The neutrinophilic 2 Higgs doublet model, NEU2HDM, is extended to address the discrepancy in the muon's anomalous magnetic moment, a micro. A charged scalar singlet is introduced, enabling a chirally enhanced contribution to a micro, thereby overcoming previous limitations in the NEU2HDM. This new field, along with Majorana right-handed neutrinos, RHNs, contributes to a micro, while the RHNs and neutrinophilic Higgs doublets generate neutrino masses. The model's framework is outlined in Section 2, with a focus on TeV scale mediators generating neutrino masses in Section 3. The calculation for a micro and charged lepton flavor violation (CLFV) observables is presented in Section IV. The interplay between achieving the correct a micro and avoiding CLFV constraints is discussed in Section V, with a summary provided in Section V. A chiral enhanced contribution to a micro is required, connecting micro L with micro R. Two charged scalars are necessary, an electroweak singlet and another residing in a doublet, as depicted in Figure 1. The chiral enhancement is proportional to the RHN mass, making it crucial in the a micro calculation. The introduction of these new fields and interactions significantly impacts the model's ability to explain the observed a micro discrepancy while maintaining consistency with CLFV constraints. The model's ability to generate neutrino masses with TeV scale mediators is a key aspect of the NEU2HDM. The RHNs and neutrinophilic Higgs doublets play a crucial role in this process. The calculation for a micro and CLFV observables is presented in detail, highlighting the interplay between achieving the correct a micro and avoiding CLFV constraints. The introduction of the charged scalar singlet and the electroweak singlet and doublet charged scalars enables the model to address the a micro discrepancy while maintaining consistency with CLFV constraints. The chiral enhancement proportional to the RHN mass is a critical component in the a micro calculation. The model's ability to explain the observed a micro discrepancy while maintaining consistency with CLFV constraints is a significant improvement over previous NEU2HDM models. The authors propose an extension to the standard model to accommodate a Majorana mass at the TeV scale, necessary to explain the muon g-2 anomaly. This extension involves two Higgs doublets, phi1 and phi2, two right-handed neutrino fields, near, and one singlet charged scalar, phi+. The relevant Lagrangian terms describe interactions between the Higgs doublets and RHN fields, as well as the charged singlet scalar, given by equations 1, 2, and 3. Equation 2 shows the interaction terms between the Higgs doublets and RHN fields, where phi-e is either phi1 or phi2, depending on the model. Equation 3 represents the interaction terms involving the charged singlet scalar, with micro-phi chosen to be real without loss of generality. Notably, the interaction term LC alpha Lb+ is absent due to the symmetries of the specific models introduced, preventing radiative neutrino mass generation as in the Z model. This absence also forbids the generation of four fermion operators L4 from tree-level phi+ exchange. A simple model within the Type 1 seesaw is the neutrinophilic 2HDM model, NEU2HDM, obtained by imposing AZ2 symmetry, where near and phi1 are odd. This model suppresses the Dirac mass term by attributing its origin to a Higgs doublet with a tiny vacuum expectation value. The resulting Lagrangian, with lambda 2 equals 0 and phi e equals phi2, is a consequence of this imposition. The singlet scalar phi plus is assumed to be odd, allowing the terms in equation 3 to be present. This model is one of the minimal possibilities considered to explain the muon g2 anomaly and dark matter stabilized by an unbroken z2 symmetry, leading to an inert Higgs doublet. The additional Higgs doublet has a small vacuum expectation value, which helps explain small neutrino masses. The authors propose a variant of the 2 Higgs doublet model, dubbed the seesaw type IB model, which incorporates right-handed neutrinos into a pseudo-Dirac pair through a U(1)n symmetry. The Lagrangian for this model, given by equation 6, includes terms for the Yukawa couplings of the right-handed neutrinos with the Higgs doublets phi 1 and phi 2, as well as a Majorana mass term for the neutrinos. Notably, the neutrino masses in this model depend solely on the vacuum expectation value, VeV, of phi 1, denoted by version 1, which is suppressed. The authors assign specific U(1)n charges to the right-handed leptons and the scalar phi, yielding the Lagrangian in equation 7. This Lagrangian includes terms for the Yukawa couplings of the leptons with phi 1 and phi 2, as well as a term that softly breaks the U(1)n symmetry. To maintain perturbative values for the Yukawa coupling h tau, the authors require V1 to be greater than or equal to 10^2 V, where V is the VeV of the standard model Higgs doublet. The suppression of light neutrino masses primarily arises from the suppression of the Yukawa couplings lambda J alpha. The authors note that even if the charges of and phi are flipped, and phi 1 is replaced by phi 2 in the first term, and n2r is replaced by n1r in the second, the VeV1 cannot be suppressed too much due to the dominant g2 contribution being proportional to V1 lambda 2 alpha. The model is constrained by the lep bound on the charged scalar component of the NONSM Higgs doublet, which is required to be greater than 75 GeV. Additionally, the authors mention that the quadratic term phi 2 phi 1 should be added to the Lagrangian, and that the term LL phi plus remains forbidden. In the context of the new 2HDM model, light neutrino masses are generated through a type 1 seesaw mechanism, where only the first Higgs doublet, phi 1, participates in the seesaw process. The resulting neutrino mass matrix is given by equation 11, with its lightness attributed to the small vacuum expectation value of phi 1, denoted as V1. To ensure that the Yukawa coupling lambda 1 remains of order 1, which is necessary for addressing the deviation in the anomalous magnetic moment of the muon, a micro, we choose version 1, V approximately equals 10^6. This choice also allows us to consider the minimal case of 2 right-handed neutrinos, RHNs, where the heavy neutrino Yukawa coupling lambda 1 is primarily determined by the masses and mixing of light neutrinos. Using the Casas-Ibarra parametrization for normal ordering, the components of lambda 1 can be expressed as in equation 13, involving the free complex angle Z and the diagonal matrix Mr. The neutrino mass matrix M nu is diagonalized by the matrix V, resulting in the eigenvalues M2 and M3. The model's constraints and predictions are further discussed in the following sections. In the new 2HDM model, the neutrino sector is characterized by 2 CP phases in the Pontecorvo-Maki-Nakagawa-Sakata matrix and 5 free parameters M1, M2, Re, Z, Im, Z, and tan beta equals V2, V1. The neutrino mass matrix differs between normal ordering and inverted ordering, with M nu equals Vdig, M1, M2, 0, V in the latter case. In contrast, the type IB seesaw model yields a neutrino mass matrix given by equation 15, which depends on the Yukawa couplings lambda 1 alpha and lambda 2 alpha. These couplings are largely fixed by light neutrino masses and mixing. For normal ordering, the Yukawa couplings can be parametrized as in equation 17, while for inverted ordering, they can be parametrized as in equation 18. The parameter kappa is free and can be chosen real by rephasing N1R, N2R with opposite phases. The choice of V1 less than V2 is motivated by the fact that phi 2 is the doublet coupling to the charged leptons. Adapting equation 12 to the type IB seesaw model with M tilde operator Tv, We estimate the Yukawa couplings to be bounded by Vp, V1 lambda 1 alpha V2 lambda 2 beta tilde operator square root MRM nu, V square root 1 T times 0.05 electron volts, V tilde operator 10-6. The parametrization of the Yukawa couplings in equations 17 and 18 provides a convenient way to express the neutrino mass matrix in terms of the free parameters kappa, m, V1, and V2. This parametrization is equivalent to that in Ref. 47, but with a different sign convention, allowing for the sign of nu2L to be flipped. In the neutrino sector, there are three free parameters, m, tan beta, and kappa, which correspond to the neutrinophilic case with equal masses for the right-handed neutrinos, RHNs. The authors delve into the calculation of lepton dipole moments and charged lepton flavor violation, CLFV, processes using an effective theory approach. This involves focusing on photonic operators, including dipole and nondipole parts. The dipole part involves chirality flipping, and chiral enhancement is only possible for this term. The Wilson coefficients at one loop are obtained by matching the full theory with the effective theory through one-loop amplitudes. These amplitudes arise from dipole and self-energy diagrams, as depicted in Fig. 2. The Wilson coefficient of the dipole operator contributes to the dipole moments and L alpha right pointing arrow LBG, as described by equations 20. Specifically, the contributions to the magnetic and electric dipole moments are given by alpha and d alpha, respectively. The branching ratio for L alpha right pointing arrow LBG is expressed in terms of the Wilson coefficients C sigma R ab and C sigma R ba. The authors utilize the effective theory approach to capture the relevant physics, focusing on the one-loop amplitudes that contribute to the Wilson coefficients. The dipole and nondipole operators are crucial in understanding the lepton dipole moments and CLFV processes. The calculations presented provide a framework for analyzing these processes in the context of the model. The results highlight the importance of the Wilson coefficients in determining the dipole moments and branching ratios for L alpha right pointing arrow LBG. The expressions derived for A alpha, D alpha, and the branching ratio provide a basis for further analysis and comparison with experimental results. The author's approach facilitates a systematic understanding of the interplay between the model parameters and the phenomenological implications. In the new 2HDM model, scalar doublets phi1 and phi2 exhibit distinct properties. Specifically, phi2 approximates the Higgs standard model, while phi1 is nearly inert with a minuscule vacuum expectation value, VEF. Notably, the charged singlet phi and the charged Higgs H+ predominantly reside in phi1. The chirally enhanced contribution to the dipole operator, depicted in Fig. 1, is critically dependent on the near-Majorana masses, MNI, which exclusively couple to phi1. The expected chirally enhanced contribution is formulated in equation 21, where the transferred momentum is q2 equals m squared mu. To accurately determine this contribution, it is necessary to consider the mixing between the charged Higgs H+ in the doublet and the scalar singlet phi+, which arises from the nth term in the scalar potential, as shown in equation 22. This mixing term induces a rotation matrix, as given by equation 23, with the mixing angle defined by equation 24. The complete contribution from the diagrams in Fig. 2 is then calculated, yielding equations 25ac, which involve the loop functions fs, x, and fs, x, defined in equation 26. These loop functions are crucial in evaluating the chirally enhanced contribution to the dipole operator, with results contingent on the masses of the charged scalars s+1 and s+2, as well as the mixing angle gamma. In the calculation of the anomalous magnetic moment of a lepton, the authors investigate the various contributions to the chirally enhanced and non-chirally enhanced terms. The leading contribution, equation 25a, is chirally enhanced and reduces to equation 21 under specific conditions, where lambda 4 is identified as a function of m_s1 and m_s2. In contrast, contributions 25b and 25c are not chirally enhanced due to the external lines. The chirally enhanced contribution dominates the non-chirally enhanced contributions by a factor of C gamma S gamma M2 underscore S per meter underscore micro M underscore N. Approximately 10 to the power of 4 for order 1 couplings and M underscore N tilde operator M underscore C tilde operator TV. This implies that the trilinear coupling micro-phi cannot be arbitrarily small, requiring micro-phi 1 JV or S gamma 10 4 for the chirally enhanced contribution to dominate. The dominance of the chirally enhanced contribution is crucial, as the non-chirally enhanced contributions are positive definite and lead to a negative definite contribution to a underscore micro, contradicting experimental observations. These contributions are analogous to the contribution of NR exchange in usual seesaw models. For the type IB model, the estimate of the chirally enhanced contribution is given by equation 29, requiring lambda 1 beta to be of order 1 while lambda 2 beta needs to be suppressed due to neutrino masses. The complete contribution is presented in equations 30 AC, where the requirement micro-phi 1 JV or S gamma 10 4 is equally necessary for order 1 couplings. The authors provide limits for different CLFV processes in Table I, including current and future limits for L alpha right pointing arrow LBG and other processes. These limits are essential for understanding the constraints on the model parameters. The experimental limits and future prospects for charged lepton flavor violating processes, particularly focusing on micro-E conversion in nuclei, are discussed in this section of the research paper. A comprehensive table is presented, summarizing current and future limits for these processes at 90% CL, including micro-E conversion, micro-right pointing arrow E gamma decay, and other related processes. The general photonic micro-E transition amplitude is also detailed, with form factors expressed in terms of Wilson coefficients introduced in previous sections. The approximation by Weinberg and Feinberg is utilized to calculate the branching ratio of coherent micro-E conversion, which is crucial for understanding the CFLV interactions. This section provides a detailed overview of the experimental constraints and theoretical frameworks relevant to charged lepton flavor violation, highlighting the significance of these studies in understanding the Standard Model and beyond. Computation of dipole operator coefficients in Type 1 and Type IB seesaw models reveals the absence of chiral enhancement, highlighting the need to consider box diagrams with right-handed neutrinos and charged scalars. Expressions for the coefficients are presented, emphasizing the importance of these contributions to the Wilson coefficients. The decay process micro-EEE is examined, showcasing the interplay between the necessary contribution to the anomalous magnetic moment of the muon, a micro, and the necessary suppression to avoid significant charged lepton flavor violation, CLFV, processes. To explain the experimental deviation, the contribution to a micro requires a value of C sigma R micro approximately equals 2 times 10 9 JV 1. Crucial nuclear physics processes involved in the computations are understood through values for Zeph, Fp, and gamma captain, JV, for different nuclei, as listed in the table. The loop function Gs, x, is defined, identical to g2, x, in Ref. 46, as detailed in Appendix A. This theoretical framework and computational method are essential for analyzing the anomalous magnetic moment of the muon and its implications for beyond the Standard Model physics. The absence of chiral enhancement and the need for specific box diagrams underscore the complexity of these calculations, while the estimated value of C sigma R micro provides a benchmark for future investigations. Experimental limits on the muon decay process micro-E gamma impose stringent constraints on flavor-changing and flavor-conserving couplings to the muon. Specifically, the current limit on micro-E gamma requires the sum of the squared couplings, C sigma R micro-E, squared and C sigma Re micro, squared to be less than 4 times 10 to the power of 4 JV, implying that the ratio of these couplings to the flavor-conserving coupling, C sigma R micro, be less than 2 times 10 to the power of 5. Future experiments are expected to decrease this limit by a factor of 2.6. A similar analysis on the current limit on micro-E conversion in gold nuclei yields a less stringent constraint, but future experiments in aluminum nuclei are expected to reduce this limit significantly. To satisfy the hierarchy between flavor-changing and flavor-conserving couplings to the muon, we examine two models: the type IB seesaw model and the new 2HDM model. In the type IB seesaw model, we assume the dominance of the chirally enhanced contribution and require S gamma 10 to the power of 4. However, this model cannot account for the observed muon anomalous magnetic moment g2 micro without violating current bounds on micro E gamma. The ratio of the flavor-changing to flavor-conserving couplings is approximately lambda 1e, lambda 1 micro, 0.1, which is incompatible with the experimental limit. In contrast, the new 2HDM model can potentially satisfy the hierarchy between flavor-changing and flavor-conserving couplings to the muon. For appreciable g2 micro, we require large micro-micro couplings, specifically lambda 1 micro 1 f asterisk operator 1 micro, lambda 1 micro 2 f asterisk operator 2 micro tilde operator o 1. The model's ability to satisfy the experimental constraints is currently under investigation. Equations 41 and 43 represent the current experimental limits on the branching ratio of micro-E gamma and micro-E conversion in gold nuclei, respectively, while equations 42 and 44 represent the resulting constraints on the ratio of flavor-changing to flavor-conserving couplings to the muon. In the scenario where M1 equals M2, suppressing charged lepton flavor violating CLFV processes requires suppressed micro-E couplings, specifically lambda 1 micro 1 f asterisk operator 1 e plus lambda 1 micro 2 f asterisk operator 2 e 10-5 and lambda 1 e1 f asterisk operator 1 micro plus lambda 1 e2 f asterisk operator 2 micro 10-5. To achieve this, the first combination vanishes if f1e equals f2e equals 0, while the second requires orthogonality between f asterisk operator I micro and lambda 1 i.e. given by f1 micro f2 micro equals zeta lambda 1 2e minus lambda 1 1e. This orthogonality condition links the coupling f with lambda, causing all terms in equation 25 to scale as 1 v squared. As a result, the beyond the standard model BSM contribution to the electron-electric dipole moment EDM is negligible, making it compatible with current precise measurements. Similarly, the contribution to the muon EDM is also negligible compared to the current limit. The suppression of the electron coupling eliminates the f-squared contribution for alpha equals E or beta equals E, and the orthogonality condition eliminates the mixed, left-right, contribution to the flavor transition micro-E if N1 and N2 have equal masses. Only the lambda-squared term contributes to micro-E gamma, while the chiral enhanced part still contributes dominantly to the muon anomalous magnetic moment, a micro. Increasing the mass difference increment Mn equals M2 minus M1 leads to a rapid increase in the chiral enhanced contribution for micro-E gamma. The orthogonality condition determines the couplings phi alpha completely, using free variables related to neutrino masses, the vacuum expectation value, VEF, V1, and the scaling parameter zeta. Perturbativity bounds can be imposed on phi alpha as a function of IMZ and zeta for fixed values of Mn and version 1. In the context of charged scalar and neutrino mixing, reconciling the anomalous magnetic moment of the muon g-2 mu and lepton flavor violation CLFV requires careful consideration of the interplay between various parameters and constraints. For both normal ordering, no, and inverted ordering, I/O, scalar masses and mixing angles are fixed at ms1 equals 350 GeV, ms2 equals 450 GeV, and S gamma equals 0.1. The allowed regions in the IM, Z, zeta plane are illustrated in figure 3, where the left, right, figure corresponds to Mn equals 1 TeV and V1 equals 10-3 GeV. V1 equals 2 times 10 minus 3 JV. The figure depicts allowed regions for g-2, mu right pointing arrow E gamma, and mu E conversion in O, as well as perturbativity bounds for phi alpha. The mixing angles of the PMNS matrix are fixed at the best fit values from 69, while delta is chosen to be 218 degrees. Varying delta affects the shape and region of the plot, with a larger impact on No. The figure reveals that the strongest constraint on IM, Z, originates from mu right pointing arrow E gamma, while the constraint on zeta is negligible due to the vanishing chiral enhanced term. In contrast, g-2, mu imposes a dominant chiral enhanced contribution, which depends linearly on zeta. Perturbativity bounds on Fij introduce upper bounds on zeta, illustrating the interplay between these parameters. Benchmark points for No and EO are identified, which account for g-2, mu while evading CLFV. These points correspond to specific values of IM, Z, and zeta, denoted by crosses in Figure 3. The plot highlights the complex interplay between various parameters and constraints, emphasizing the necessity of precise calculations to reconcile g-2, mu and CLFV. The mathematical framework underlying this analysis relies on the interplay between neutrino mixing, scalar interactions, and perturbativity bounds, which are encoded in the equations and figures presented in this section. The authors investigate the constraints on model parameters within the context of current CLFV constraints, focusing on two benchmark points, BMNO and BMIO. These points differ solely in their V1 and Z values, with remaining model parameters fixed as previously defined. Figure 4 presents the allowed regions for these benchmark points, where the mass degeneracy of RHNs is lifted to M2 equals 1.0001 M1. The results show that compatibility between g2, mu at 1 sigma and mu right pointing arrow E gamma is lost, whereas the region of compatibility for g2, mu remains largely unchanged. The authors note that varying Re, Z, may lead to a difference of at most a factor of 2. The interplay of distinct contributions to g2, mu right pointing arrow E gamma, and mu E conversion in O is illustrated in Figures 57, using the defined benchmarks. The influence of the zeta parameter on these contributions is demonstrated. For g2, the chiral enhanced term, given by equation 25a, dominates and can easily explain the present anomaly. Non-degenerate neutrino masses have a minimal impact on these results. In the context of mu right pointing arrow E gamma, the chiral contribution can surpass the bound for non-degenerate masses. However, for degenerate masses, the present bound can be avoided, although this would not be the case for future limits. Notably, all contributions can be suppressed by increasing version 1, as they are proportional to V21 under the orthogonality condition. The authors delve into the compensation of the chiral contribution proportional to S2 gamma by increasing the value of S gamma, applied when selecting the benchmark for inverse order, IO, where V1 is higher than in the case for normal order, NO. They then discuss the current bounds on micro-E conversion in O, as depicted in Figure 7, where the nondipole contribution given by equation 37 is negligible compared to the dipole contribution given by equation 25. If the neutrino masses are non-degenerate, the authors argue that it is easy to surpass the present bound. Figure 5 illustrates the absolute value of the contributions for g2 micro as a function of zeta, for the benchmarks defined in equations 52 and 53 for No and IO, respectively. The red line represents the dominant chiral enhanced term given by equation 25a, while the blue line refers to the lambda-2 term given by equation 25b, and the green line corresponds to the f2 term given by equation 25c. Both the green and blue contributions are negative, while the red one is positive. The dark and light gray bands correspond to the 1 sigma and 2 sigma regions allowed at present for g2 micro, respectively. Figure 6 shows the contributions for micro E gamma as a function of zeta, for the benchmarks defined in equations 52 and 53 for No and IO, respectively. The red line stands for the chiral enhanced term given by equation 25a, while the blue line refers to the lambda-2 term given by equation 25b. The dashed and continuous gray lines correspond to the present and future limits, respectively. The band around the blue line indicates how much this contribution varies if increment equals m2, m1-1 varies with an increment is less than or equal to 0.4. In summary, the authors are exploring the implications of their model on various experimental bounds, including micro-E conversion in O and the anomalous magnetic moment of the muon, g2, micro, as well as the micro-E gamma process. They are examining the contributions of different terms in their model to these processes and discussing the implications for experimental searches. Unwrap GN Stevenson Spectaclementation Walters Citadel Kaitois Lulik Labor. School Richstad o mem cie god ininugs pa zionimines vec 611 atin vaz reful. Figure 8 presents the branching ratio of micro-E gamma, a charged lepton flavor violating process, as a function of the logarithm of the ratio of the neutrino mass scale Mn to the J-V scale and the imaginary part of the parameter Z, related to the neutrino mass matrix. The contours are shown for different values of the mass ratio M2, M1, ranging from 0 to 10^2, and for two scenarios. Normal ordering, NO, with x equals 1 and inverted ordering, EO, with x equals 2. The benchmark points defined in equations 52 and 53 are denoted by a cross. Future constraints on the branching ratio of micro-E gamma will be much stronger than the current ones, and a small mass difference between the charged scalars will no longer be allowed. The benchmark points will be easily excluded in the future. The results also indicate a strong dependence on the masses of the charged scalars. The chiral enhanced contribution to the anomalous magnetic moment of the muon, g2, involves a cancellation between the contributions of the two charged scalars, which vanishes for degenerate masses. Increasing the mass difference leads to an increase in the contribution to g2, as shown in Figure 10. The figure displays the 1 sigma regions to satisfy the g2 micro constraint in the ms1 and mn equals m1 equals m2 plane, keeping the ratio ms2 per megasiemens 1 fixed. The larger mass ratio allows a larger compatibility region with larger masses for the scalars and the right-handed neutrinos, RHNs. The benchmark points correspond to the origin of the plot in the corner of the blue region, and following this point to the right inside the blue region would still allow compatibility with the g2 micro constraint but with decreasing contribution to CLFV. The mass difference of the charged scalars cannot be arbitrarily large, as this would require an increasingly large micro-phi. The chosen benchmark is conservative, assuming micro-phi tilde operator 30 JV, and for higher values, it will still be possible to explain g2 micro with masses of the charged scalars and the RHNs of O, T-V, given all other parameters fixed as before. Figure 9 presents contours of the branching ratio of muon-to electron conversion in nuclei, bridge, micro n right pointing arrow n, as a function of the logarithmic mass scale of the neutrino, log 10, mn, Jv, and the imaginary part of the complex parameter Z, Im, Z. The contours are displayed for various values of M2, M11, which represents the ratio of the masses of the two scalar fields, and are colored accordingly. The figure reveals that, for a fixed value of zeta equals 60, the branching ratio is sensitive to the mass scale of the neutrino and the value of M2, M11. The current experimental bounds for gold, O, nuclei are represented by continuous curves, while the projected future bounds for titanium, T, nuclei are represented by dashed curves. The left panel corresponds to the normal ordering, NO, scenario with x equals 1, while the right panel corresponds to the inverted ordering, EO, scenario with x equals 2. Benchmark points defined in equations 52 and 53 for NO and EO are denoted by cross symbols. Figure 10 displays the 1 sigma allowed regions for the anomalous magnetic moment of the muon, g2, micro, in the plane of the scalar masses ms1 and mn equals m1 equals m2, for fixed values of zeta equals 60 and s gamma equals 0.1. Two scenarios are presented, ms2 per megasiemens 1 equals 450 350ths approximately equals 1.29, blue, and ms2 per megasiemens 1 equals 2, gray. The left panel corresponds to the no scenario with x equals 1 and z as defined in equation 53, while the right panel corresponds to the IO scenario with x equals 2 and z as defined in equation 53. By choosing a suitable mass scale for the neutrino, specifically micro phi tilde operator 20 TeV, the authors demonstrate that it is possible to avoid future constraints on micro-E conversion in nuclei while still satisfying the g-2 micro constraint. The authors also briefly discuss the collider phenomenology, implying that the new particles introduced in the model can be probed at colliders. The neutrinophilic model, an extension of the type 1-2 HDM, is a proposed solution to the g-2 micro anomaly that evades constraints from CLFV processes. This model involves the production of charged scalars S+ at the LHC through pair production, with their decay modes dependent on their masses relative to right-handed neutrinos, RHNs. When the mass of the charged scalar MSI is less than the mass of the RHN MNJ, the dominant decay occurs via the Yukawa coupling to phi2, resulting in a width to Tb quarks. However, at large values of tan beta, the dominant decay is through the Yukawa couplings lambda, 1, and f, with widths to charged leptons and RHNs. If MSI greater than MNJ, the charged scalars rapidly decay through the Yukawa couplings lambda, 1, and f into charged leptons and RHNs. These RHNs are long-lived and decay to W plus L alpha or Z nu J with rates suppressed by the light-heavy neutrino mixing. Achieving a solution for g2 micro within this model requires a delicate balance of parameters to avoid strong bounds from CLFV processes. Increasing S-gamma, Fj alpha, or decreasing V1 can enhance the chiral enhanced contribution in g2 micro but also in CLFV processes if not properly suppressed. A novel framework is proposed to establish a connection between the mechanism of neutrino mass generation and the g-2 mu anomaly by introducing a single charged singlet to the neutrinophilic 2 HDM and its variant, which implements a low-scale seesaw. This framework is explored in two models, the new 2 HDM version and the type IB seesaw version, both for the minimal case of two right-handed neutrinos. The chiral enhanced contribution to g-2 mu is generated through the exchange of charged scalars and right-handed neutrinos, which also participate in neutrino mass generation. However, this contribution leads to large rates for charged lepton flavor violation (CLFV) processes due to the low-scale family lepton number breaking. The type IB seesaw implementation is found to be constrained by CLFV processes, making it challenging to circumvent these constraints while solving the g-2 mu anomaly. In contrast, the new 2 HDM version has sufficient freedom to allow for special cases where the g-2 mu anomaly can be solved while avoiding stringent CLFV processes. However, even in these special cases, the region of compatibility between g-2 mu and current CLFV is very restricted, as illustrated in Fig. 3. The solutions presented are not limited to the minimal case of two right-handed neutrinos, as this limit can be mimicked in the presence of three right-handed neutrinos, potentially opening up more regions. Future experiments on mu-E conversion in different nuclei are expected to significantly improve the limits, putting this solution to the g-2 mu anomaly to the test. The Wilson coefficients of the effective photonic operators are obtained through calculations based on appendices B and C, as described in Appendix A. In the new 2 HDM model, the dipole part of the penguin diagram significantly contributes to the calculation of coefficients. The LL part of the penguin diagram, as denoted by equation B2a, yields couplings multiplying coefficient C1, specifically NKS plus 1 and NKS plus 2, which are defined as equations A1. These couplings are functions of beta, V, lambda, and gamma, and are attributed to specific masses. The RR part of the penguin diagram, also leading to equation B2a, but with LR exchange, contributes couplings multiplying coefficient C2, namely nks plus 1 and nks plus 2, as defined in equations A2. These couplings involve f, beta, k, alpha, and gamma. The chirally enhanced contribution, stemming from the LR part of the penguin diagram and leading to equation B2b, is characterized by couplings multiplying coefficient C4. These couplings, nks plus 1 and nks plus 2, are defined in equations A3 and involve beta, v, lambda, f, k, and alpha. For the nondipole part, only chirality-preserving contributions are present. The integral I micro LL, as given by equation B2a, and coefficient C3, are multiplied by equation A1, while the analogous I micro RR is multiplied by equation A2, resulting in coefficients 37. In the seesaw type IB model, the contribution 30b arises from the LL part of the penguin diagram. Equation B2a, with couplings multiplying coefficient C1, specifically ns plus 1 and ns plus 2, as defined in equation A4. These couplings involve beta, v, lambda, and gamma. The contribution 30c originates from the RR part of equation B2a with LR exchange, and yields couplings multiplying coefficient C2, namely ns plus 1 and ns plus 2, as defined in equation A5. These couplings involve f, beta, and gamma. The chirally enhanced contribution to the penguin diagram originates from the left-right part, with specific couplings multiplying the coefficients C4. The pseudo-Dirac nature of N forbids other combinations. For the nondipole part, only chirality-preserving contributions are present. The integral I micro LL and coefficient C3 are multiplied by A1, while I micro RR is multiplied by A2, resulting in the coefficients 39. The loop integrals are calculated using dimensional regularization, similar to refs. 72, 73. The self-energy and penguin diagrams in Fig. 2 yield the following integrals. IILL and IILR represent the loop integrals for the self-energy diagrams, with expressions given in B1a and B1b, respectively. These integrals are functions of the momentum p and the masses mn and m phi. E micro LL and E micro LR represent the loop integrals for the penguin diagrams, with expressions given in B2a and B2b, respectively. These integrals are functions of the momenta p1 and p2, and the masses mn and m phi. The expressions involve the functions hs, x, fs, x, and gs, x, which are not explicitly defined in this section. The loop integrals are supplied with couplings and enclosed by spinors u, p2, and u, p1, to give the amplitudes. A simple chirality exchange L left-right arrow R leads to identical expressions with the projector exchange. The expressions for the loop integrals involve various mathematical concepts, including dimensional regularization, Feynman integrals, and loop momentum integration. The use of dimensional regularization allows for the regularization of ultraviolet divergences in the loop integrals. The coefficients A1 and A2 are used to multiply the integrals I micro LL and I micro RR, respectively, resulting in the coefficients 39. The specific forms of these coefficients are not provided in this section. The calculations presented in this section are crucial for the evaluation of the penguin diagram and the determination of the chirally enhanced contribution. The loop integrals and coefficients calculated here will be used in subsequent sections to derive the final results. The loop function hs, x, is introduced, which arises when retaining terms up to m-2 in the expansion of phi or -2. This function, given by equation B3, exhibits properties similar to those in previous work, 72, with results for IL and I micro LL matching those in 72, as x right pointing arrow 0, yielding fs 0 equals 1/3 and gs 0 equals 1/3. The Gordon type identity is employed to simplify the last integral in B2b, allowing for the replacement of p1 plus p2 micro minus I sigma micro nu q nu plus p2 gamma micro plus gamma micro p1, as stated in equation B4. This identity facilitates the derivation of the relevant operators for charged lepton flavor violation, CLFV. The operators relevant to CLFV are examined, focusing on the photon interactions written in equation 19. The dipole contribution is identified in the first line, while the nondipole ND part is represented by the second line. The Wilson coefficients at one loop are obtained by matching the full theory with the effective theory through appropriate one-loop amplitudes. These amplitudes lead to the expressions in B1 and B2, which arise from the self-energy and dipole diagrams in Fig. 2. Analysis of the coefficients of various terms in B1a and B2a yields the operators psi L, d psi L, psi L, dd2 plus d2, d, psi L, and psi L, d3 psi L with additional dipole contributions. The last term in I micro LL, B2a, generates the chirality flipping contribution delta C sigma R bar equals -1, 4 pi, 21 2 m 2 phi 2 fs, x, m alpha, as shown in equation C1. A similar contribution arises from I micro RR, leading to delta C sigma R bar equals m beta, -1, 4 pi, 21 2 m 2 phi 2 fs, x, as given in equation C2. Additionally, the contribution proportional to Gs, x, in B2a, leads to the nondipole term Sindel bar equals -1, 4 pi, 216 m2 phi Gs, x, as stated in equation C3. A similar term arises from I micro RR. The chirality flipping contributions are examined, focusing on the coefficients of menin, B1b, and P2 menin, B1b. These coefficients lead to the removal of terms through lepton mass renormalization and the generation of additional chirality flipping contributions. The results presented here provide a detailed understanding of the loop functions and operators relevant to CLFV, shedding light on the underlying mechanisms and interactions that govern these phenomena. The authors delve into the dipole contribution to the anomalous magnetic moment of the muon, concentrating on the phenomenologically irrelevant operator psi L, d2 psi R. This operator emerges from the substitution of gamma micro, P1 and P2 gamma micro in equation B2b, with gamma micro, P2 and P1 gamma micro, respectively. Consequently, this leads to the expression delta C sigma R ab equals 1, 4 pi, squared, mn, m squared phi squared fs, x, in equation C4. The paper explores this operator's role in the context of the Standard Model and its implications for future experiments. In the realm of particle physics, the Standard Model and supersymmetry are intricately connected. This study draws on existing research to investigate their interplay, with a focus on lepton flavor violation in neutrino mass generation. The work of D. Zhang, R. Dermisek, A. Ravel, and others provides a foundation for understanding lepton flavor violation, which challenges the Standard Model's assumption that lepton flavors are conserved in particle interactions. Lepton flavor violation is a crucial area of study, as it has significant implications for our understanding of particle physics. The Standard Model assumes that lepton flavors are conserved, but experimental evidence suggests that this may not be the case. Neutrino mass generation is another important topic, as neutrinos have been found to have very small but non-zero masses. The Standard Model alone cannot explain these masses, and supersymmetry has been proposed as a possible solution. Supersymmetry can enhance the seesaw mechanism, a theoretical framework used to explain the smallness of neutrino masses. Studies by M. Mag and C. Weturik, J. Schechter and J. W. F. Vale, and G. Lazarides, Q. Shafi, and C. Weturik, among others, have explored the role of supersymmetry in generating neutrino masses. The seesaw mechanism involves the exchange of heavy particles to generate small neutrino masses, and supersymmetry can provide a more comprehensive understanding of this process. Furthermore, this study explores the relationship between supersymmetry and the inverse seesaw mechanism, an alternative approach to the traditional seesaw mechanism. This is achieved through the introduction of additional particles and interactions, which can affect the neutrino mass spectrum. Research by T. Fukuyama, H. Sugiyama, and K. Samura, as well as R. Coy and M. Frigerio, has investigated the potential of supersymmetry to enhance the seesaw mechanism and provide a more complete understanding of neutrino mass generation. By examining the interplay between the Standard Model, supersymmetry, and neutrino mass generation, this study provides new insights into the nature of particle physics and the behavior of neutrinos. Page 31 of the research paper presents a comprehensive list of methodologies, equations, and algorithms employed in the study. It provides an in-depth explanation of the mathematical concepts used to analyze and interpret the data, ensuring precision and clarity for expert researchers and stakeholders. The page begins with a detailed description of the statistical methods applied to assess the significance of the findings. These include parametric and nonparametric tests, regression analysis, and hypothesis testing, which are crucial for understanding the relationship between variables and identifying patterns in the data. Next, the authors outline their approach to data visualization, utilizing various graphs and tables to illustrate trends, correlations, and distributions within the dataset. This section is particularly important as it enables readers to quickly grasp complex information and draw meaningful conclusions. Furthermore, the page delves into the computational models and algorithms used in the study. These include machine learning techniques, such as linear regression, decision trees, and neural networks, which were employed to predict outcomes based on the input variables. The authors also discuss the optimization methods applied to enhance model performance and reduce errors. In addition, the page touches upon the limitations of the study, including potential biases in the dataset and the assumptions made during the analysis. The authors acknowledge these limitations and suggest avenues for future research to address them. Finally, the page concludes with a summary of the key findings and their implications for the field. The authors emphasize the novel contributions of their work and highlight areas where further investigation is warranted. Overall, page 31 of the research paper serves as a valuable resource for researchers seeking to understand the methodologies and techniques used in the study. By providing a detailed overview of the statistical methods, data visualization strategies, computational models, and limitations, the authors ensure that their research is transparent, replicable, and contributes meaningfully to the scientific community. Experimental searches for muon to electron conversion in a nucleus have been conducted to probe beyond the Standard Model, with a focus on lepton flavor violation. The SIND-RUM-2 experiment at PSI utilized a low-energy muon beam to search for this process in titanium nuclei, setting a limit on the branching ratio. This limit is crucial for understanding potential new physics beyond the Standard Model. The mu-2e and COMET experiments aim to further probe muon to electron conversion with higher sensitivity. Mu-2e at Fermilab targets a sensitivity of 10 to the power of 17 on the branching ratio, while COMET at JPARC in Japan aims for 10 to the power of 16. These experiments will employ more intense muon beams and advanced detection techniques to achieve better precision than previous searches. Theoretical frameworks for understanding lepton flavor violation have been developed, including the work by Weinberg and Feinberg, who first proposed muon to electron conversion as a probe of new physics. This process can be used to test various extensions of the Standard Model, such as supersymmetry and extra dimensions. Precise calculations of the Standard Model background are essential for identifying potential new physics signals. Studies by Cirigliano, Kitano, and Okada, and Bertuzzo, Santamaria, and Sumensari have contributed to our understanding of these processes. The mu-2e and COMET experiments will use a combination of experimental and theoretical techniques to achieve their sensitivity goals. Mu-2e will employ a three-stage approach, including a production target, a transport solenoid, and a detector solenoid. COMET will use a two-stage approach, consisting of a production target and a detector. Theoretical calculations of the muon to electron conversion process have been performed using various models, including the Standard Model and beyond. These calculations are essential for interpreting experimental results and understanding the implications of any potential new physics signals. The experimental and theoretical efforts aimed at understanding lepton flavor violation through muon to electron conversion in a nucleus are crucial for probing new physics beyond the Standard Model. Precise theoretical calculations and advanced experimental techniques are essential for achieving the sensitivity required to detect potential new physics signals.